Let's talk about data analysis and some statistical models as we move forward. Alright, so test statistics, what is it? Basically what we're trying to do when we test a statistical model is to see whether or not the data that we've collected is a significant fit to that model. So some of the things that we look at when we're talking about a test statistic So any test statistic that we will use is essentially the variance that is explained by the model divided by the variance that's not explained by the model, which is really just simply saying it's systematic variation divided by unsystematic variation. And that really is nothing more than the effect divided by the error. So that pretty much explains, what the test statistic will look like. And it doesn't matter if it's a t-test, ANOVA, anything. This is essentially what the test statistic states. When we talk about frequency distributions, we generally refer to this as a histogram. So the frequency is on the y-axis and the observations are on the x-axis. And we like to compare that frequency distribution to a bell-shaped curve, otherwise known as the normal distribution. So here we've got the traditional bell-shaped curve. Where we have the vast majority of the data. Will essentially lie around the center of the distribution. And then as scores deviate from that center or the mean, the frequencies decrease. Alright, so that's essentially the bell-shaped distribution. And when we look at this, we want essentially 99% of our data to fall within 2.58 standard deviations from the mean, and 95% to fall within plus or minus 1.96 standard deviations from the mean. And so when we talk about 95%, that's where we usually, we talk a lot about 1.96, and that is because it correlates to 95% of a level of confidence. Here's just a picture of the frequency distribution with the normal distribution overlaid on top of it. And what we do is we use these histograms to be able to tell whether our data collected is normal or not. And you can see all the deviations from normality fall into these spots here. And so the question always becomes, it's subjective, whether or not a data set is normal or not. And we can use those empty spaces to find out whether it is normal or not. So if it's not normal, it usually deviates from normality in a couple of ways. We have skewness and kurtosis. So skew is associated with the lack of skew, or positive skew, which is so positive skew, we have the scores or the data is really bunched at low values, and we have a tail that points to the higher values. And then on the opposite side of that is negative skew, where we have the scores bunch at the high values and the tail points to the low values. The other way we can deviate from normality is kurtosis. And kurtosis is essentially the pointiness of the curve. We can also refer to it as the heaviness of the tail. And there's two ways to really describe this. Leptokurtic and plateokurtic. So plateokurtic is flat. So essentially you've got a very flat distribution. And leptokurtic is you have a very, very tall, very pointed distribution. Some central tendency definitions. We essentially have the mean, which is the average of our data collection. The mode is something that most frequently occurs. And the median is the middle data point. Sometimes it's called the 50th percentile. The median is great because it's really not affected by extremes. So if you had a data set and there were 2 or 3 values that were really, really off, that would really impact your average score or your mean score. However, the median would kind of throw those 3 away and it wouldn't be impacted. So sometimes it's important to use the median for analysis as opposed to the mean. In terms of mode, we really don't like having bimodal data or multimodal data. And this picture here really shows a picture of bimodal data. Dispersion is really the spread of the distribution or the range. Obviously this is affected by extremes as well. So if we've got 11 Facebook users and we're going to count the number of friends that they have, the range is 220, but we essentially have what we would call outliers. And when you look at it, this 252 really does change the range as well as the mean of all of those friends and the number of the friends of the Facebook users. We can also look at quartiles where you have 25th, 75th, and 50th percentile. So the upper quartile is really the 75th percentile, lower quartile is the 25th percent, and then the second quartile is in the middle or the median, so that's the 50th percentile quartile. In terms of the normal distribution, there's some really basic properties. It's pretty unimodal. It's also symmetrical about the mean. As we already discussed before, it is bell-shaped and it has the maximum height at the mean. It is continuous. It is also asymptotic to the x-axis, meaning, sorry about that, the farther away from the mean, the closer it gets to the x-axis, but it never really touches the x-axis. It has zero skewness and zero kurtosis. So those are the basic properties of a normal distribution. Now the problem is we have an infinite number of combinations. That could really explain any type of distribution. So we have to be able to look at the standard normal distribution to be able to say whether or not that data set is really normal or not. And so how you do that, you essentially transform the raw data with a z-score. So every data point, x being your data point, x bar being your mean, and s is your standard deviation of that sample, you can convert every individual data point into a z-score. And like we already said before, that 1.96 cuts off the top 2.5% or the bottom 2.5%, depending upon whether it is positive or negative. And then we already talked about 99% falling between the 2.58. And then if you really want to get critical, 99.9 is plus or minus 3.29. So when we look at statistical models, we really want to try to classify them, whether it's a good fit, whether it's a moderate fit, or whether it's a poor fit. And that's all we're trying to do. We're trying to statistically say whether within a 95% level of confidence if it's a good fit or not. So when we're doing our statistical analyses, the possibility of collecting data on a population is almost nearly impossible. So a population would be everybody or everything that falls within that category, collecting all the data points on that. There's time constraints, there's financial constraints, it usually cannot be done. So because we can't collect data on the entire population, we usually collect something that is within our time and financial budget, and that's a sample. So it's a smaller collection of units that's just taken from that population. So essentially we've got the outcome will be equal to the model plus the error. So when we're collecting that data, the first thing that we do is we always determine the mean, or the average of that sample. So that's essentially our first statistical model, is simply that the outcome is equal to the mean plus or minus some error. Now that mean is technically just a hypothetical value. It doesn't really exist in the data set. It's pretty simple to calculate, and it's also the value from which the standard scores or the squared scores deviate the least, so it's got the least error. And so that's why it's really chosen as the very first statistical model. Now a deviation is trying to assess the fit of that mean, and the deviation is just the difference between the actual data point and the mean of the data set. So to really look at more of that fit of that mean is, right, the x bars are data point minus the mean. The sum of those, set that equal to 0. And what ends up happening is we end up with any deviations from the mean end up canceling out, because some deviations are positive and some deviations are negative. So in order for our deviations not to cancel out, we actually need to square those deviations. And when we square those deviations, it's now called the sum of squared errors, because the deviation is just another word for error. Alright, so the sum of squares, it is a little bit better measure of our data set, particularly for overall variability. And the only problem is that it's somewhat dependent on the number of our data points. And so we can say, all right, well, what is our average variability for a sample set? Well, we just need to take our sum of squares and divide it by n minus 1. And that n minus 1 is essentially what we're going to end up calling our degrees of freedom. And the sum of squares divided by n minus 1 is what we actually call our variance. Now the variance has one problem. they're in squared units. So I don't know about you, but I don't know what squared miles per hour means. So it's really not meaningful. But if we take the square root of that variance, what is that going to tell us, right? That's really going to tell us what the average error is between our population mean and our sample mean. So what that's really telling us is how well does this mean, or the mean could be considered just another model type. And then that average error is essentially what we're going to end up calling our standard deviation. So now we've got these three pieces. We've got the sum of squares, the variance, and the standard deviation, essentially representing the same thing. It's all just the fit of the model. It's the variability. How well does the model represent the data, and what error is there with that model? Now let's look at something that has the same mean, but it has a different standard deviation. And this is why the standard deviation is a little bit a better tool to be able to describe our sample set. So it has the same mean. There's about the mean. There's about the mean. Same mean, but this data set, right, we have some pretty big dispersion. And here we don't have very much dispersion. You know, our data set goes essentially from 25 to 85. And here it's 0 to probably over 100. That's a pretty big range. So that's why it's really nice to use the standard deviation. Now, degrees of freedom, what does this really mean? So we've got the number of observations that are free to vary is what we're going to call our degrees of freedom. So if you're going to use a population, your degrees of freedom is essentially going to be equal to the number of data points you have. But as we talked about, that's kind of nearly impossible to be able to collect that. So we're usually always going to be using a sample. So to calculate the standard deviation, so if we want to find S, we need to use the sample mean to be able to estimate the population mean. So we need to hold one parameter constant, so if we're going to hold one parameter constant, that means the number of observations that are free to vary will be our sample minus the mean that we're holding constant, which is 1. So that pretty much will hold true for the vast majority of all the statistics that we'll do this semester.